All right, your deep learning exam is tomorrow, so let's cut right to the chase. This is your final cram session on one of the most important topics you're going to face, explainable AI, or XAI. We're going to cover everything you need to absolutely nail this part of the test. So let's just start with a fundamental question. We spend all this time building these amazing, super powerful AI models, but what's their single biggest flaw? It's not about speed, it's not about accuracy, it's something else. And the answer is, they're black boxes. We feed data in one end, we get an answer out the other end, but what happens in the middle? The actual why behind the decision? It's a complete mystery. And that mystery is the entire reason the field of XAI even exists. And hey, this isn't just some academic thought experiment. The data proves it. Look at this. On the left, you see interest in deep learning hitting its peak and starting to level off. And right at that exact moment, look at the right. Interest in explainable AI just goes vertical. It explodes. The second we perfected these powerful tools, we immediately realized, we have no idea how they actually work. Okay, so here's our game plan for this study session. We'll start with the black box problem. Then we'll nail down the key definitions. You'll definitely see these on the exam. We'll look at the whole XAI landscape, check out a few specific methods, and then wrap up with why this all matters so much. All right, part one, let's really dig in and make sure we all get what this black box challenge is really about. The root of the problem is just the mind-boggling scale. We're not talking about a simple equation. We are talking about a web of millions, sometimes billions, of tiny little knobs and dials all interconnected. Trying to follow a single decision through that, it's like trying to follow one specific drop of water through the entire ocean. It's practically impossible. The source material has this fantastic analogy you should definitely remember for the exam. It compares a neural network to those Russian matryoshka dolls. To understand it, you have to keep opening layer after nested layer of complex math. It's functions inside of functions inside of functions. Okay, pay attention. This chart right here, you need to burn this into your brain. It is absolutely crucial. It shows the basic trade-off in all of machine learning. See up here in the top left? That's deep learning. Super high accuracy, but basically zero interpretability. Down on the bottom right, simple models, like a basic decision tree. Yeah, you can understand it, but it's way less powerful. The whole goal of XAI is to live in that top right corner, to get the best of both worlds. Okay, moving on to part two. Let's lock in some key terms. Seriously, get these definitions right, and you're looking at some easy points on the test. First up, transparency. This one is pretty much what it sounds like. A model is transparent if you can just look at it and see how it works. That little decision tree is the perfect example. You can literally trace the logic with your finger. It's the complete opposite of a black box. Next, you have interpretability. Now, this is a step up. It's not just about seeing the whole model. It's about being able to provide a meaningful story for what the model did. So we might not understand every single parameter, but we can explain its decision in a way that a human can actually understand. And finally, we get to the big one, explainability. You should think of this as the gold standard. It goes beyond just understanding. It's about creating a dialogue between the person and the AI. An explainable system isn't just accurate and interpretable. It's a system that can justify itself and build real trust with us. The National Institute of Standards and Technology, NIST, they boiled it all down to 4 principles you should know. A good explanation has to be 1, provided in the first place. 2, it has to be meaningful to the person asking. 3, it must be an accurate reflection of how the model actually works. And 4, and this one is so important, it has to know its own limits. It has to be able to say, hey, I'm not so sure about this one. So with those definitions in our back pocket, how do we actually do this stuff? Let's move to part 3 and get a map of the whole XAI world. This flowchart is basically your field guide, so let's just walk through it. At the very top, you have 2 choices. You're either starting with an opaque model, a black box, or a transparent model that's already easy to understand. The key takeaway here is this path. When you start with that black box, you have to use something called a post hoc method to try and figure it out. And that brings us to another must-know distinction for the exam, post hoc versus intrinsic. Intrinsic models are the easy ones. They're just born that way. They are explainable by design. Post hoc methods, well, that's when you have to play detective. The model is already built, it's a black box, and you're using these special tools after the fact to try and peek inside. Now, within those detective tools, those post hoc methods, you've got one more split. Is the tool model agnostic? Think of this like a Swiss Army knife. It's flexible. You can apply it to almost any model out there. Or is it model specific? That's more like a special key, right? It's designed to unlock one and only one type of model architecture, like how GradCam is built just for CNNs.
Okay, part 4. We have the map, we know the categories. Now let's just quickly touch on a few of the actual techniques you're likely to hear about.
Now, don't worry, you probably won't have to code these for the test, but you should recognize the names and know what they do. So there's Lime, which cleverly explains one specific prediction by building a simple little model just for that one area. You've got Shop, which uses principles from game theory to give every single feature an important score. And then there's GradCam, which produces those really cool heat maps showing you exactly what pixels an image recognition model was focusing on. And that brings us to our final section. We've covered the what and the how, but now we have to talk about the why. Why is this whole field exploding? Well, the stakes could not be higher. This quote really says it all. This isn't just a fun academic puzzle anymore. AI is making decisions in medicine, in the justice system, in finance. Being able to explain those decisions is becoming a legal, social, and ethical requirement. And this table just drives the point home. I mean, think about it. Would you trust an AI that diagnoses cancer if it can't tell you why it thinks you have it? How do we make sure an algorithm used in court isn't racially biased if we can't look inside? And if a self-driving car gets into an accident, we absolutely have to be able to explain the life or death decision it made. Unexplained answers just aren't good enough anymore. So when you boil it all down, that's the grand vision here. XAI is all about building a bridge. It's a bridge between the incredibly powerful but alien way a machine thinks and the way we humans think. It's about finally turning these black box tools into true partners we can understand and trust. So I'll leave you with this final thought to take into your exam and into your career. As AI gets smarter and takes on more responsibility, maybe its most important feature isn't its accuracy or its power, but simply our ability to understand it. Okay, that's everything you need. You're ready.